Good afternoon, Ma. Today we are going to see allotropic forms of phosphorus and the other compounds of phosphorus like phosgene, phosphorus trichloride, phosphorus pentachloride, all their preparation, properties, structures, and uses, all that we'll discuss. Last class, I hope you all remember what all we discussed. We saw the structure of oxyacids of nitrogen. So, like around 6 structures, we discussed on how to draw the structure. In a simple way, we discussed in last class. I hope you are all thorough in that now because that will be asked in 2 mark or 3 mark definitely. Today we are going to see allotropic forms of phosphorus. Allotrope means what? Same chemical formula but different physical state. Yes or no? So phosphorus have several allotropic modification of which the three forms, namely white, red and black phosphorus, are most common. So in nature, allotropes of sulfur are more in number, but most common one are white, red and black. So the freshly prepared white phosphorus is colorless but becomes pale yellow due to the formation of layer of red phosphorus upon standing. So this is very simple, we can understand this. Hence it is also known as yellow phosphorus. So it is poisonous in nature and has a characteristics of an garlic smell. So all these could be asked in objectives. It glows in dark due to the oxidation which is called phosphorescence. So in dark, what does it will do? It starts to glow. That property we call it as an phosphorescence. Its ignition temperature is very low and hence it undergoes spontaneous combustion in air at room temperature to give phosphorus pentoxide. The white phosphorus can be changed into red phosphorus by heating it into 420 degrees Celsius in the absence of air and light. Unlike white phosphorus, it is not poisonous at all and it does not show any phosphorence. So these are comparative nature. So what is the difference between white phosphorus and red phosphorus? White phosphorus is poisonous and red phosphorus is not poisonous. So that exhibit phosphorescence white phosphorus but red phosphorus will not do. It also does not ignite at low temperature. The phosphorus can be converted into white phosphorus by boiling it in an inert atmosphere and condensing the vapor under water. So these two paragraphs when you combine, you can see the difference between white phosphorus and red phosphorus. The phosphorus as a layer structure also act as a semiconductor. அதுக்கு structure எப்படி இருக்கு? Layer, one by one layered structure இருக்கு. It also acts as a semiconductor. The 4 atoms in phosphorus have polymeric structure which with the chains of P4 linked tetrahedrally. So this is what tetrahedrally they are linked together. Unlike nitrogen, P triple bond P is less stable than P single bond P. That is, P triple bond P bond is less stable than the single bond phosphorus. So hence phosphorus atoms are linked through single bonds rather than triple bonds. So why they are linked to single bonds? Triple bonds are not stable. In addition to the above, 2 more allotropes, namely scarlet and violet phosphorus, are also known for phosphorus allotropes. Apart from white, red and yellow, we have scarlet and violet phosphorus also. This is the structure. And what are the properties? Phosphorus is highly reactive and has the following important chemical properties. First is reaction with oxygen. So yellow phosphorus readily catches fire in air and give dense white fumes of phosphorus pentoxide. So what is yellow phosphorus? It forms a pale layer on standing white phosphorus. Then only yellow phosphorus is formed. So readily it catches fire with oxygen and it gives the dense white fumes of phosphorus pentoxide. Same way red phosphorus also reacts with oxygen to give phosphorus trioxide or phosphorus pentoxide, as you can see the equation here. So phosphorus reacts with oxygen, it gives phosphorus trioxide P2O3. And then if you see with the phosphorus pentoxide, it is also reacting white phosphorus and red phosphorus. Reaction with chlorine. Phosphorus reacts with chlorine to form tri and pentachloride. Yellow phosphorus reacts violently at room temperature while red phosphorus reacts on heating only. So these are all the, it may look very simple, but they may ask an objective. Yellow phosphorus reacts violently at room temperature itself, whereas the red phosphorus reacts very slowly on heating. And reaction with alkali, yellow phosphorus reacts with alkali on boiling and it in an inert atmosphere, liberating phosphine. So here phosphorus acts as an reducing agent because oxygen is getting added to the, hydrogen is added to phosphorus, so it acts as an reducing agent. So P4 is phosphorus reacts with an alkali sodium hydroxide in the presence of water. You will get sodium hypophosphite with phosgene liberated. Reaction with the nitric acid, when phosphorus is treated with concentrated nitric acid, it is oxidized to phosphoric acid. So nitric acid would react panona, it will get converted into orthophosphoric acid. So here we will use iodine crystals as a catalyst. Then with metals like calcium, magnesium, it gives phosphites like magnesium phosphide, calcium phosphide. And metals like sodium and potassium react with phosphorus vigorously, which means they are highly reactive metals. Next is uses of phosphorus. The red phosphorus is used in matchboxes, we all know very well, and it is also used for the production of certain alloys like phosphor bronze. Next is phosphine. Phosphine is the most important hydride of phosphorus. PH3 is phosphine. It is a hydride of phosphorus. It can be prepared by the action of sodium hydroxide with white phosphorus in the inert atmosphere of carbon dioxide or hydrogen. So phosphorus reacts with alkali with carbon dioxide or hydrogen. We will get sodium hypophosphite and phosgene. Phosgene is freed from phosphine dihydride, that is P2H4, by passing through a freezing mixture. So the dihydrate condenses while phosgene does not. So it will have some other byproducts also, not only phosgene. So here phosphine comes out with P2H4, that is phosphine dihydrate. So we have to pass that through any freezing mixture, so that phosphine alone will be coming outside, the other one get frozen. Phosphine can also be prepared by hydrolysis of metallic phosphites with water or dilute minerals. So calcium phosphide reacts with water to give phosphine. Same way aluminum phosphide reacts with dilute acids like hydrochloric acid to give phosphine, and it is also prepared in pure form by heating phosphorus acid. So when you heat phosphorus acid, you will get hot orthophosphorus acid and phosphine. A pure sample of phosphine is prepared by heating phosphonium iodide with caustic soda. So caustic soda is nothing but sodium hydroxide, and caustic potash means potassium hydroxide. Here they are given caustic soda, it is sodium hydroxide solution. Here we have to use phosphonium iodide to give phosphine, and sodium iodide and water as a byproduct. What are the physical properties? It is colorless poisonous gas with rotten fish smell. It is slightly soluble in water and is neutral to litmus. So it condenses to a liquid, that is a colorless liquid, at 188 Kelvin and freezes to a solid at 139.5 Kelvin. Next is chemical properties. Phosphine decomposes into its elements when heated in the absence of air. So we have to heat that in the absence of air at 317 Kelvin, or when electric current is passed through it, we will get a decomposed product of phosphine like phosphorus and hydrogen gas. Next is combustion. When phosphine is heated with air or oxygen, it burns to give a metaphosphoric acid. Phosphine reacts with oxygen to give phosphorus pentoxide, as well as the same phosphorus pentoxide reacts with water to give metaphosphoric acid. Next is basic nature. Phosphine is weakly basic and forms phosphonium salts with halogen acids. So phosphine reacts with hydrogen iodide. So any halogen acid we have to take, so that we will get phosphonium iodide, and that same phosphonium iodide reacts with water to give phosphine, hydronium ion and iodide ion. It reacts with halogen also to give phosphorus pentahalides. So phosphine reacts with chlorine to give phosphorus pentachloride. Its reducing property, phosphine precipitates some metals from their salt solution, like silver nitrate reacts with phosphine to give silver phosphite, and then nitric acid. It also forms a coordination compounds with Lewis acids like boron trichloride. So boron trichloride reacts with phosphine to give a coordinated compound where phosphine donates a both the pair of electron to form a coordinated bond between boron and phosphorus. It forms a complex, and this is its structure. In phosphine, phosphorus shows sp3 hybridization because we can see 3 sigma bonds and one lone pair. Well, we consider that also a sigma bond. If we have 4 pairs of bond here, we will take it as 1s and 3p. So it is sp3 hybridized the phosphorus here, and 3 orbitals are occupied by bond pair, and 4th corner is occupied by lone pair of electrons. So here we are having 3 bond pairs, like with the phosphorus and hydrogen bond, which is 1.42 angstrom, and one lone pair, and because of that lone pair only our bond angle is reduced to 93.5 actually, and phosphine has a pyramidal shape. Uses of phosphine: phosphine is used for producing smoke screen as it gives large smoke. So how it is going to give large smoke? Usually this is used in ships and all. In a ship, a pierced container with a mixture of calcium carbide. Pierced container means which has a hole in that. A carbide, calcium carbide and calcium phosphide liberates phosphine and acetylene when thrown into sea. So they will have this container with a mixture of calcium carbide and calcium phosphide. So when that is thrown into a water, what will happen? It liberates phosphine gas and acetylene when thrown into the sea. So it liberates phosphine, which catches fire and ignites the acetylene. So we all know phosphine reacts with oxygen readily. So at room temperature itself, any temperature, so it will catches fire there. So it will act as an igniting property. This phosphine will act as an igniting agent and it will catches fire to the acetylene. Acetylene is a good flammable substance. So these burning gases serves as a signal to approaching ships. This is known as a home signal. So they will readily have this a container, a mixture of calcium carbide and calcium phosphide. So this could be asked in 2 mark, very important use of phosphine. So when that is thrown into water, it will get fire by igniting the acetylene by liberating the phosphine. Next is phosphorus trichloride and phosphorus pentachloride. Phosphorus trichloride preparation is when a slow stream of chlorine is passed over white phosphorus, phosphorus trichloride is formed. It can also be treated with the thionyl chloride. So when we pass this chlorine gas through white phosphorus, it forms phosphorus trichloride. Or otherwise it can also be prepared with what? Thionyl chloride. What is thionyl chloride? SOCl2 is thionyl chloride. It gives phosphorus trichloride. Its properties: it is hydrolyzed with cold water. It gives a phosphorus acid. That is H3PO3. This reaction involves the coordination of water molecule using a vacant 3d orbital on the phosphorus. So already we saw we have a vacant 3d orbital in phosphorus atom, following by the elimination of HCl, which is similar to the hydrolysis of silicon tetrachloride. So phosphorus trichloride reacts with water to give an adduct product, which is PCl3 with one water molecule. It gives POHCl2 and hydrochloric acid, and this reaction is followed by 2 more steps, like HPOCl2 reacts with water to give H2PO2Cl2, that is along with the byproduct as water. Same way it reacts with water also to give H3PO3 and phosphorus acid. Similar reaction occurs with other molecules that contains alcohols and carboxylic acid. So here if you take ethanol, you will get an ethane chloride, and if you take this acid, you will get an ethanoate chloride. And then uses of phosphorus trichloride. Phosphorus trichloride is used as a chlorinating agent and for the preparation of H3PO3 also. phosphorus pentachloride. If you see the structure, first we'll complete the structure of phosphorus trichloride. So can you see the structure of phosphorus trichloride, PCl3? So the bond angle is 100 degrees and it is also a pyramid, looking like a pyramidal in shape. It is same like phosphine. Phosphorus pentachloride preparation, when PCl3 is treated with excess chlorine, you will get this phosphorus pentachloride, and chemical properties, it reacts, or on heating it decomposes. This PCl5 will get decomposed to phosphorus trichloride and chlorine gas. And phosphorus pentachloride reacts with water to give phosphoryl chloride and orthophosphoric acid. So PCl5 reacts with water to give phosphoryl chloride, which reacts with water to give orthophosphoric acid. The overall reaction is given. Phosphorus pentachloride reacts with metal to give metal chlorides. It also chlorinates organic compounds similar to phosphorus trichloride. So it reacts similarly to phosphorus trichloride. So anywhere whatever, it is also going to give a chlorinated product only. It reacts with silver to give silver chloride, tin chloride, ethanol chloride, and then ethane, chloroethane. So uses of phosphorus pentachlorides are, they are used as a chlorinating agent and is very useful for replacing hydroxyl groups by chlorine atom. Next is moving on to the structure, very important, structures of oxides and oxoacids of phosphorus. Phosphorus forms phosphorus trioxide, phosphorus tetroxide and phosphorus pentoxides. In phosphorus trioxide, phosphorus atoms lie at the corners of the tetrahedron and 6 oxygen atoms belong to the edges. So can you see here, the 4 phosphorus, they are occupying the tetrahedron, that is given in pink color, and the 6 oxygen will occupy all these corners, and the PO bond end distance is 165.6, and which is shorter than the single bond distance of PO. So here PO bond distance is 165.6, but the actual bond length, it should be 184 picometer, because it is lesser than the actual bond length. This is due to pi d pi bonding and results in the considerable double bond character. So the P4O10 also forms 3 bonds to oxygen atom and also additional coordinate bond with the oxygen atom, and terminal PO bond length is 143 picometer. Can you see here, and which is less than the expected single bond distance like in the other molecule. This is also due to the lateral overlap of the filled p orbitals of oxygen atom with empty d orbital on the phosphorus. So there are 2 exceptions. They are differing from the actual PO bond length in P4O6 and P4O10 both. So you have to remember the reason for that, why it is lesser than the actual bond length. One is P2O6 is p pi d pi bonding. Here it is the lateral overlap of filled p orbital of an oxygen to the empty d orbital on the phosphorus. With this we'll stop today. The next class we will discuss the structure. It is also very simple, like how we discussed for the oxides and oxyacids of nitrogen. So we will see this structure and this preparation, and then we'll move on to the group 16. Now today we have discussed the phosphorus pentachloride, phosphorus trichloride, and then phosphine and the allotropes of phosphorus. So many important points are given in these paragraphs, especially in the allotropes, and in the structures and uses are very important. So go through the chapter very carefully. So here and all, when it comes, you may ask, I have to remember all these equations, and you may ask, no need. Very important, preparation of phosphine, preparation of phosphorus pentachloride and phosphorus trichloride, obviously you have to remember, and then uses you have to remember, and the structure you have to remember, and then the physical properties. So all this, if you remember, means it's more than enough. That's why I didn't go deep into this. And also the important part here is allotropes. It is having so many objectives in that paragraph, so go through that allotropes paragraph also. Apart from that, no need to go deep into this. Is it clear? Mostly we will cover up with the book back itself. Do your assignments and send on time. Thank you.